Okay, so the first application I want to show you for exponential growth is very topical. It's for infectious diseases, and that comes with a couple caveats. Um, One is that new infectious diseases that pop up, they aren't necessarily are they aren't necessarily I wouldn't even say aren't necessarily. They aren't pure exponential curves. They're only partially exponential curves. Um, so um, let's say that new infectious diseases infect people in a truly exponential way. If that were to happen, then let's say our x-axis is time, and let's say our y-axis is number of infections. Number of infections. I don't know how to spell. So number of infections, there we go. So let's assume that, let's assume incorrectly that diseases, new infectious diseases, grow in a purely exponential way. If we assume this, then let's look at what happens. We'll start our exponential curve here at t equals 0, and we'll see that, in the beginning of our outbreak for our new disease, the growth rate is quite small, right? The growth rate is quite small because the number of people infected, usually at the beginning, is pretty small. But as the number of people infected increases, and if there are no, successful intervention strategies, and the disease is just allowed to grow and grow and grow, let's just assume incorrectly that this exponential growth increases and just keeps on going and keeps on going and keeps on going and keeps on going and keeps on going, and maybe eventually we'll see a problem, right? Maybe eventually we'll see, we'll notice that this is not realistic, because maybe on this y-axis for the number of people infected, maybe at this particular value we have around 7 billion. And around 7 billion is a key number because that's around the world population, 7 to 8 billion people. And so if we believe that new infectious diseases are purely exponential in their growth, then we would have to have more people infected than the current world population. So that's the main caveat here. Infectious diseases are a great application of exponential growth, but we have to realize that it's not a pure exponential curve, because eventually we start to run into some issues that will decrease the rate of growth, right? And one issue is that there are only a certain number of people that can be infected. Another issue is that interventions can happen. Like eventually you'll run out of new people to infect, so the growth rate will decrease, and eventually it will peak, and then the number of people infected will start to decrease. And so we get this kind of different curve with a peak. So for the application part of it, what we could look at, or what we could say, is that this is really the exponential growth section of the curve. So infectious diseases can be modeled partially with exponential growth and exponential functions, at least at the beginning of an outbreak, when interventions are relatively small and the disease is still growing pretty fast. And I will talk a little bit also about this peak. Now, let's say at this y-axis for the number of people infected, let's say at this particular number of people infected, maybe at this particular number of people, maybe that is the limiting capacity of hospitals, right? Maybe hospitals can't treat maybe hospitals can't treat a higher number of people than this. And so if that's true, then as soon as we get to this part of the curve, as soon as at the time, t, that we get to this part of the curve, all of a sudden, we're going to be over our hospital capacity, and that's going to be an issue because if hospitals can't treat and accept everybody who's sick, including people who aren't even sick with this particular infectious disease, right? Because people are still going to be going to the hospital for other reasons, like maybe the flu or like a broken leg or other reasons, right? So if the rate of infection goes way beyond the capacity of hospitals to deal with it, then that's going to be an issue, right? So what we are seeing in the news is this phrase, which is called flattening the curve. And what we want when we flatten the curve is to perform interventions so that the growth rate isn't as high. So if we are flattening the curve, then the curve will be less steep, and hopefully, let's see if I can do a decent drawing of this. Hopefully, if we can flatten the curve enough, then we can keep the peak, the peak of this curve below the capacity of hospitals to deal with it. So that would make it so that we have successful interventions here. Right here, we have a new peak, and this peak is below hospital capacity. So our healthcare system would not be overloaded if the growth rate were flattened, right? If the steepness of that curve were flattened. So what could we do to decrease the rate of exponential growth here? Well, to decrease the rate of exponential growth, we have a few interventions that we can do that you've probably heard of. So one of them is social distancing and limiting contact with each other so that the disease cannot spread from person to person as effectively. Therefore, the growth rate would decrease, and correspondingly, the graph of the infection curve would flatten here. So this exponential portion of the curve would flatten, and then we would get a lower peak, hopefully below hospital capacity. You can do things like improving basic hygiene so that even if the virus does come into contact with you, it will be less likely to actually infect you. You would have washed your hands before you touched your eyes or face or nose or mouth. You can identify and isolate cases if you have good testing capacity, right? You can identify who is sick and isolate them so that you can limit the spread to the general population. And you can do travel restrictions as well. If there's a localized outbreak, you can limit travel to and from that particular location, which is really only effective if the infectious disease has not already spread to other locations. And this here is a great video that I would suggest you watch if you have extra time, which goes on even more about the math of COVID-19 and the spread of infectious diseases as well. So that is an application of exponential growth. And in the next video, we're going to start looking at exponential decay.